you don't have to follow me. You can keep it here. It started. Okay, good. Okay. So this is lesson number 2 for exponents, right? It goes on these pages in your comp book, and it starts with like terms. So let's put this up. CLT. What does CLT stand for? Everybody say combine like terms. This goes way back in your math training, right? Way back, I don't know how many years now, but you've been combining like terms for quite some time. Okay, so now we're going to go back through that and talk about that again. Yes, so let's spell it out. Combine like terms. So, are these two terms like terms? X squared, or x to the power 2, plus x cubed, or x to the power 3. Are these like terms? Right? This is your question. Interestingly enough, it's the addition here, the operation of addition, that brings into this like terms discussion. If we were multiplying these, we wouldn't care, we can multiply. In fact, if you think about our prior lesson, we did multiply these, right? So just off to the side here, if this is x squared times, let's put a dot in there, x cubed, this is x times x, that's what x squared is. X times x times x is 3 of these, right? And it's times, so what do you have? We were able to add the powers and say this is x to the 5th, it's 5 x's. The big difference here is we switch to addition operation. So addition and subtraction now brings into this topic combine like terms. We can't add items that are not like terms. So in this case, these are not like terms. You can't combine these when we're talking about addition, right? So if you said no to this, you were correct. If you said yes, I feel for you too, because this is kind of complicated. Your brain doesn't always register this, right? You're thinking, hey, they're both x's, right? They're both base x. But what we need to have like terms for addition for this, they would need to be the same power also. Okay, and we'll see that. We'll get to some examples. So, if somebody gave you this problem, then they said equals and said simplify it, here's the only thing you can do. You just rewrite it. It can't be combined in any way. It has to sit there separate and just put a plus between it. Are you with me on that? Okay, so let's go down a little bit further and get to this. CLT review, combine like terms. Let's add 2x and 3x. So what is 2x? First of all, are 2x and 3x like terms? Why? What's different about these that we said they're not? What's happening here that we say they are? And let me ask you this. Let me lead you a little bit with some leading questions. What's the power on the x here? What's a power on an x? It just sits there. I don't see a power. Is there a power? It's a 1, right? So there's an invisible 1 here. What's the power on this x? 1. So they're like terms because they share that same power. And just a quick review of remember the 3 invisible 1s way back from last semester? Anytime, let's say you have an x just sitting here, there's an invisible 1 here, an invisible 1 here, 1 times that, an invisible 1 here divided by that. It's called the 3 invisible 1s. We're not going to write them every time because we as mathematicians or people doing math, right? We want to make this simplified. We just want to write x. Any number also, say it was a 5. 5 has 3 invisible 1s. 1 here, and 1 here, right? That's why every number is a fraction in some sense, right? Because everything's over 1, there's a numerator position and a denominator. Even if I write 5, it's sitting in the numerator position all the time, which is another difficult thing when students start working with fractions. There seems to be this middle position. Like if you see 3 and 1/2, my brain is very confused. The 3 looks like it's right in the middle, right? There's no middle position. So what position is the 3? Is it numerator or denominator? What's it got to be? Given the 3 invisible 1s discussion, where does the 3 have to be? What position? Got to be numerator. You with me? Got to be. Because under here is sitting a 1, and that pushes it up, so now it's the same level as that 1. Does this make sense? But we do everything we can to confuse you by saying, oh, it's 3.5. It looks good when we write it. but it confuses our brain in terms of what position that number's sitting in. Okay, a little bit off topic, but now that we know these are like terms, can you combine them? What do you get? How many x's you got here? How many? Trust yourself. 2, right? I know, you're like, how many x's do I have? You got 2, there's 2 x's there. How many you got here? 3. Yep, trust yourself. And so if you combine them, how many you got?
5.
Yeah, good. All right? And the problem is your brain is switching between this operation with addition and subtraction and this setup with multiplication and division. They're completely opposite. And your brain has to literally change gears to go between those, right? And it's why you always can learn it. And if you get a lot of these problems, you'll do great. If you got a lot of these, you'll do great. But if they start to get mixed on a page, your brain has a lot of trouble switching between them because they're different rule sets. All right. Let's go to the next one. 5x squared minus 2x squared. So 5x squared minus 2x squared equals. Number 1, are they like terms? How many say yes? Okay. Okay. How many say I don't know? Be brave. Okay. How many say no? Anybody want to go no? So the majority of you are saying yes, they're like terms. You're right, because why? They're both base x and they're both power 2. That makes them like terms. There's 5 of them here, 5x squareds, there's 2 here, and we're subtracting them. What are you left with? The 3 of them that are x squareds. Fair enough? Once you get into the rhythm of like terms, it gets to be pretty simple. All right, let's take it up a notch, and let's say x cubed plus 3x squared (2x squared plus 6x) I don't know why my brain can't remember this right now, but I have to keep looking at it. Minus 5x equals. Okay. So now we're jumping from 2 like terms, right? We knew they were like terms. Now we're looking a little bit different. Are there any other x cubes in this statement? No. So this is the only one of its kind, right? In terms of combined like terms, this is a unique one. Are there any other x squareds? Yes, this one right here. They're like terms, so they have to be joined together, right? Are there any other x's? Yes, the 5x. So what we're going to do is combine, we're going to run through this thing, combine the like terms portions of it. These are like terms, and these are like terms. There we go. So the x cubed stays here, it's in the statement. A 3x squared and a 2x squared is plus 5x squared. A 6x minus a 5x is 1x, and it's still positive. That's the simplification or the combining of the like terms of that statement. Okay. Next example, let's see if I can go remember this one a little bit easier. 8c squared minus 3d squared. Okay, can you see up here? 8c squared minus 3d squared. Oh, help me out here. Thank you so much. Plus, parentheses, 6c what?
6 squared.
Okay. Go ahead.
Minus 3cd plus 7d squared.
Oh, minus 3cd?
Yeah.
Nice.
And then plus 7d squared.
Again?
7d squared. 7d squared.
Like that?
Yeah.
Yeah, I don't know why. My brain's not functioning right now. And check it over for me. Do I have it written right? Okay, thank you guys. I appreciate that so much. Okay, so what's going on here? The parentheses start to give us potential issues, right? Anytime there's a sign outside of a parentheses, it will be distributed over those terms inside the parentheses, but since it's a positive, that's not going to cause us any problem here. If it were a minus here, the minus would have to be distributed across these, but it's not. Do we have any other, so effectively speaking, we could remove these parentheses from this statement because there's nothing going on that requires these. So we could go like this, literally here, on this particular one. And it would be better if I rewrote it, but I'm just a little bit too lazy, so if I remove that. Are there any other c squareds? Here and here, right? These two. What's 8c squared plus 6c squared? 14c squared. Are there any other d squareds? Yes, right here. So these have to be combined. This is CLT. 7d squared minus 3 leaves us with plus 4d squared. And the CD, there's nothing else with both CD in it, so it's here on the tail. And sometimes we'll write this a different way. We probably would have liked to have seen this written this way. Okay, let's see what else they give us. Okay, read this one to me. Ready, Barry?
Is that an S?
I know, right? The tail says it's an S, otherwise it starts to look like a 5 for me.
Okay, 3S squared plus
3S squared plus
2S, is it T?
2ST
Plus 5T squared.
plus 5T squared.
Yes.
Okay, parentheses?
Yeah.
That's it? What else? Do this from it. Subtract this from it. Minus
2S squared.
2S squared
ST plus 7T squared. Is that?
plus ST?
Yeah.
Okay. Plus ST. Say
Plus 7T squared.
7T squared. Parentheses. Good. Okay. So here, because there's a minus sign in front of a parentheses, this is like saying minus 1 times everything in this distributed. So this has to be distributed across this statement. And it's like saying plus, the minus goes here. So minus 1 times this would make this minus 2s squared. The minus here would be minus st. The minus here would be minus 7t squared. And now it's back to a plus statement, where we can effectively remove the parentheses again. So, oops. So now these can be removed because everything's been distributed across these, right? So we can go like this for them and kind of effectively take this out. And probably I would rather rewrite it, but I'm going to run out of space. So how about other s squareds? There's a 3s squared here. Any other s squareds here? Here. So these two have to be combined because they're both s squared. 3s squared minus a 2s squared leaves you with a 1s squared. Do we have two STs? Here's an ST and here's an ST. So 2ST minus an ST would leave us with plus 1ST. The 5t squared minus 7t squared goes into the negative range here, so it's going to be a minus 2t squared. And this is the combining like terms of this process. Does this make sense? So you're asking, are they like terms? And because you're dealing with addition and subtraction, they will be for this set. The problem comes in if we're mixing it up with multiplication or division. Here. Good. Good. Combining like terms, subtracting. Subtraction is actually multiplying. Interesting. Okay. That's what we did in front of the parentheses. And degree of a polynomial is in this one. So, and polynomials. So review some vocabulary. What is a polynomial? It's a multi-term statement. So the fact that we have these different terms, each one of these being called a term, a poly, what does poly mean?
More than one?
More than one. Yeah, I think another way might be able to say many, right? Poly means many. Nomial means terms in this case is the easiest way to think of it. So now you're into these algebraic statements that are polynomic, right? There's more than one, there's two. Now this one was simplified to one, but this one remained. How many terms? So there's different things here. There's the degree of it and the number of terms. Terms and degree of a polynomial. Degree is the largest power. So this would be a third degree because that's the largest power. In terms of terms, this would be a 3-term polynomial because there's 3, 1, 2, 3 there. And we take it after we reduce it in terms of combining like terms. All right? There's some problems in here to do. Practice them yourself and then compare them back. The answers are in the notes. See them buried in there. So when you practice them, you can have the answer and figure out if it's correct.